An immense pleasure. Dr. Anuradha Gupta is an associate professor at Department of Mathematics, Delhi College of Arts and Commerce, University of Delhi. Ma'am has done BA Honours Mathematics from Janki Devi Memorial College, University of Delhi, and MA Mathematics from Hansraj College, University of Delhi. Ma'am has completed MPhil and PhD from University of Delhi. Her specialization areas include operator theory, functional analysis, and fixed point theory. Ma'am holds an experience of over 30 years in teaching and research. Dr. Anuradha Gupta has published more than 65 papers in various journals of international repute. Ma'am has authored 4 books. Ma'am is a reviewer of various reputed international journals. Ma'am has delivered numerous invited lectures in various conferences across the world, such as Romania, Austria, USA, and Turkey. Ma'am has undertaken research projects funded by UGC. Ma'am has organized various summer schools at University of Delhi. Under her supervision, 10 students have completed their PhD and currently 6 are pursuing their PhD under her supervision. I would like to express my sincere thanks to Dr. Anuradha Gupta, who was my PhD supervisor, for her constant support, encouragement, and her invaluable guidance. Those innumerable meetings, despite from the research, we have discussed various issues in life, which has instilled a self-confidence and a way to look at things in an optimistic way. Ma'am has spent countless hours in proofreading my research articles and discussing new ideas. I can never thank her for all what she has done for me, but still, I want to say thank you, ma'am. Now, I request you, ma'am, to please start the session.
Thank you, Dr. Ravila, for the nice introduction. First of all,
good morning, ma'am.
Good morning.
Namaskar, ma'am.
Namaskar, namaskar. First of all, I want to thank JC Bose University for giving me this opportunity to share my knowledge and complex analysis. I want to thank the chairperson of the Department of Mathematics, Professor Neetu Gupta, and the Dean of Dean of Sciences, Professor Deekshit, the Vice Chancellor, the Registrar of the University. Complex analysis. Shall I start my lecture now?
Yes, ma'am. Yes.
Okay, thank you. I want to share the screen. Why it is not showing board today? Is it visible?
Yes, ma'am, it is visible.
Okay. The topic which I'm going to cover today is a short history of complex numbers, the Cauchy-Riemann equations, and the applications of Cauchy-Riemann equations. As Professor Gupta has explained that it has various applications in this field of science and technology, and even mathematics also. We can solve the equations using complex analysis. We can also find the contour integration using the concept of residue and the singularities. We can also integrate the complicated functions in terms of complex numbers. And I can see the students are attending this workshop. If you want to go for higher studies, means if you want to do research in mathematics, then complex analysis plays very important role. When we start about the history of the complex numbers, there is a myth about this that when the mathematicians were solving the quadratic equation x square plus 1 is equal to 0, then obviously this is -1, and then under root of -1 came into existence. This is a myth. No, this is not correct. Actually, you know that need is the mother of invention. Of course, the mathematicians were solving the equations, but it was not quadratic equation, it was a cubic equation. And during the 18th century, there was a mathematician, Al-Khwarizmi. He gave solutions of quadratic equations of various types, which we are using nowadays in schools while teaching mathematics. So various types, quadratic equation of various types, but using geometry. Now, after this, when he gave solutions of quadratic equation, there was an Italian mathematician, Latin, and he translated the work of Al-Khwarizmi in Latin. During this time, he was Gerard of Cremona. And he also translated the work of Leonardo da Pisa, famously known as Fibonacci. Basically, Fibonacci means son of Benacci. Actually, his name was Leonardo da Pisa. And Fibonacci sequences, you know, that we have the sequence of the type 1, 1, 2, 3, 5, 8, and so on. When we use the previous two, we get the Fibonacci sequence. So, Gerard, he translated the work of Leonardo da Pisa also in 12. Shall I erase this? In 1225, when the king Frederick II, he was holding a court in Sicily, and Leonardo da Pisa, he was introduced to him because during that time, the courtiers of the king was scientists, mathematicians, historians, etc. So Leonardo da Pisa was presented before the emperor, and then at that time, one problem was solved before the emperor. It was of the form x cubed plus 2x squared plus 10x plus 20 is equal to 20. This cubic equation was solved. And based on this, there was a problem that if we have a general equation, cubic equation, x cubed plus ax squared plus bx plus c is equal to 0, and it was reduced to a simpler equation by substituting x dash is equal to x plus 1 by 3 of a. When we substitute this, then this equation will reduce to x cubed plus px plus q is equal to 0. Now, this equation was tried to solve with all positive coefficients and positive values of x. With positive coefficients and positive values of x. Now, based on this, 3 cases arose. First case, the first problem was that is it possible to solve this type of equation that we have x cubed plus px is equal to q? The second was x cubed plus px is equal to px plus q. Third was x cubed plus q is equal to px. And then mathematicians were trying to solve these 3 equations to solve cubic equations. Now, there was a mathematician, Scipiano del Ferro. He was professor in University of Bologna in the year 1526. He was solving these three equations, but in the year 1526, he got the solution of the first equation. It was x cube plus px is equal to q. But he was not able to give the proof to the entire world. So in his deathbed, he gave the proof of this cubic equation in the form of a proof to his student. He was Antonio Mario Fiori. So in a mathematical contest, Antonio challenged Tartaglia. You know, he is also a mathematician of 16th century, Tartaglia. So they were facing, they had to appear in a mathematical contest. And in that contest, before the night of the contest, Tartaglia gave another proof of solving this equation, and he won the contest. Then after that, Tartaglia, he had a contract with Gerolamo Cardano, and they signed an oath of secrecy. Later on, Cardano felt that no, the credit should go to the Scipiano Ferrero, and he contacted his family. And he tried to wrote a paper in which the first author, he gave credit to Ferrero because basically he solved the problem and gave the proof to his student, Antonio Maria. Okay, but Garellano wrote a very interesting book, which is famous book. This is Ars Magna in the year 1545. And he published a formula to solve all the three equations. Which I wrote. Then they were facing solving the problem, difficulty in solving the second case, which was not based on the solution of 1. So what they did, they substituted x is equal to u plus v, and into this equation, x cube is equal to px plus q, the second equation. Then they obtained that x cube minus px, this can be written as a u cube plus v cube plus 3uv, u plus v minus p times u plus v, and this is equal to q. If you just see that if you substitute 3uv is equal to p, then obviously we get this is p, then this is equal to this, they get cancelled, and we have what? Q is equal to u cube plus v cube. So you can see that Q can be written as the sum of the cubes of u and v, and this p is the 3 times the product of u and v. So from here, what happens that if we take u cube, v cube, this is coming out to be p cube upon 27. So it means the product of the cube of the product is p cube by 27, and there's sum of the cubes of the u and v. This is q. So using these things, shall I erase, Manu?
Yes, ma'am, you can.
So using this, it was obtained that x can be written as u plus v, and its value is half of q plus w raised to the power 1 by 3 plus half of q minus w raised to the power 1 by 3. So it was obtained that W is nothing but half of Q cube minus 1 by 3 P cube. This is known as cases irreducible irreducibilis. This was the name given to this. But Cardano avoided this discussion in his book Ars Magna. Then Cardano was first to introduce the complex number of the form a plus under root of minus b. But still it was written as under root of minus b. The iota was not introduced till 1545. In the chapter 37 of Ars Magna, he posed one problem that can you find out two numbers x and y such that their sum is 10 and their product is 40. But it was not possible to find out that their sum is 10 and product is 40. So what happened that after solving this, he came to the conclusion that the solution can be 5 plus under root of minus 15 and 5 minus under root of minus 15. Because when you add, you are getting 10, and when you multiply, when you multiply these two numbers, what you get? This is 25 plus 15, which is equal to 40. But it came in the form of under root of minus 15. So that is why looking upon this, he introduced that a complex number can be written in the form a plus under root of minus b. During the 16th century, there was a mathematician, Raphael Bombelli, and he authored one book. It is known as L'Algebra. And in fact, it has 3 volumes. And he introduced the notation under root of minus 1, and he called this as Q D Meno. This name was given to under root of minus 1. And he discussed in his book to solve the cubics in L'Algebra, it was of the form x cube is equal to 15x plus 4. And he gave the solution using the Cardan's formula that it can be 2 plus under root of minus 121 raised to the power 1 by 3 plus 2 minus under root of minus 121 raised to the power 1 by 3. That this is the solution of this cubic equation. And he observed that when we put x is equal to 4, x is equal to 4 also gives us the solution of this equation. So after that, during 17th century, in the beginning of 17th century, there was another mathematician, R. Descartes. He was a philosopher, and he wrote a manuscript, La Geometria, and in this book, he introduced the applications of algebra to geometry, and from which nowadays we are using the form which is known as Cartesian geometry. We have x-axis and y-axis. Basically, Descartes introduced this to the world that the algebra can be used in geometry. And Descartes was pressed by his friends to publish his ideas, and he wrote a treatise on science under the title Discours de la méthode pour bien conduire sa raison et chercher la vérité. And later on, 3 appendices were also included in this. John Wallis in the end of 17th century introduced the negative numbers, because till the end of the 17th century, negative numbers were not into recognition, because mathematicians were thinking that negative numbers are false. They have no use. But he introduced that before zero, we can have -1, -2, -3. So with this, the set of integers were introduced. And also he gave geometrical interpretation of under root of -1. Now, in the middle of the 17th century and in the beginning of 18th century, there was another mathematician, which is known mathematician. It is Abraham de Moivre. After his name, you know the famous de Moivre's theorem that if we have cos theta plus iota sine theta raised to the power n, we can write this to be cos n theta plus iota sine n theta. Okay, so basically, he came into contact with Newton in 1698. 1698, he became friend with Newton, and in 1676, basically he proved this. But de Moivre knew that somehow Newton has already proved this, that cos theta plus iota sine theta raised to the power n is equal to cos n theta plus iota sine n theta. But he never got any credit for this. L. Euler, he first introduced iota for under root of -1. And he visualized complex numbers as points with rectangular coordinates, but did not give any satisfactory foundation for the complex numbers. Euler also used that we can write x plus iota y, a complex number, in the form r cos theta plus iota sine theta. He was the first to give this representation for complex numbers. He also defined that we can have exponential e iota theta as cos theta plus iota sine theta. Jean Robert Argand, he was a Persian bookkeeper, and nothing is available whether he was a mathematician or not, or he had any formal knowledge about mathematics. But he first expressed that we can write x, the complex number, in the form of the ordered pair, and we can represent this graphically. So that is why when we represent complex numbers, it is known as Argand plane. William W.R. Hamilton, he wrote a memoir and expressed that the ordered pair of real numbers AB, he introduced this ordered pair, and he introduced that when we add these two ordered pair, then this is nothing but A plus C, B plus D. This is nothing but the addition of the complex number. And he also introduced that when we multiply two ordered pairs AB and CD, then this is coming out to be AC minus BD and BC plus AD. This is algebraic definition of the complex numbers. So Hamilton gave the first algebraic definition of complex numbers. The development in the complex number, the actual credit goes to Carl Friedrich Gauss. Famous mathematician in 19th century. And Gauss basically gave a representation, geometrical representation of complex numbers during 1796. And he published in this Royal Society of Göttingen in 1831. and introduced the term complex numbers. Mathematicians were writing that a plus iota b is something, but the name complex numbers, it was given by Gauss, that a plus iota b, all the numbers of the form where a and b are real numbers and iota is nothing but under root of -1, these are known as complex numbers. In a letter to Bessel, Gauss mentioned in 1811, he wrote a letter to Bessel and he mentioned, which is later on known as Cauchy's theorem. Because it was unpublished, then Cauchy rediscovered it. So I'm going to tell you about Cauchy's theorem also in complex numbers. Therefore, the credit goes to Cauchy, not to Gauss, because it was not published in his name, but Cauchy published, that is why it is in his name, the Cauchy's theorem. Actual development was done by Augustus Louis Cauchy. During 1789 to 1857, basically Cauchy introduced the complex function theory. He defined complex functions, that if the domain is the set of real numbers and the range is this, then we can have a function fx which has the range of the form ux plus iota vx. So the complex function theory, the credit goes to Augustus Louis Cauchy. And he published his articles in 1825, in which the first time the contour integration was published. Okay, so this was the brief history of complex numbers. And actually, there are so many research articles published on the history, but a beautiful article was published by Orlando Merino in 2006 on the history of complex numbers from University of Rhode Island. So I have given a brief history using his paper. Let me move towards the brief introduction of complex numbers. Basically, complex numbers, this is the set of all those numbers of the form a plus iota b, where a and b are real numbers and iota is nothing but the square root of -1. And it can be expressed as the ordered pair, AB. So if suppose this is A, the ordered pair of AB, we join it with the origin, we draw perpendicular on the positive direction of x-axis, then obviously this is A and this is B. And we have this angle theta. This is denoted by R, which is known as the modulus of the complex number. And this, by using the Pythagoras theorem, R is nothing but under root of A square plus B square, which is the modulus of, if we write this to be Z, modulus of the complex number. Theta is known as the argument. Now, if alpha is any real number and we have a complex number Z, normally we write Z as a complex number. Obviously, this is of the form x plus iota v y, where x and y are real numbers. Then alpha Z, this is nothing but the multiplication of the real and imaginary part. This x from here, this is known as the real part of Z, and y is the imaginary part of Z. We multiply real and imaginary part of this with alpha, this constant. So in this way, we have the scalar multiplication. if we want to add two complex numbers, say Z1 and Z2, Z1 is X1 plus iota Y1 and Z2 as X2 plus iota Y2. This Z1 plus Z2 is nothing but the addition of real with real and imaginary with imaginary, which was introduced earlier. So this is X1 plus X2 plus iota Y1 plus Y2. We denote by Z bar the conjugate of the complex number. So this is X plus iota, X minus iota Y. Just change the sign of the imaginary part. If you multiply Z1 bar with Z2, what happens? We are getting this to be X1 minus Y1, X2 plus iota Y2. And what is this? This is X1, X2 plus Y1, Y2. This is the real part of this, real part. So this is nothing but the real part of Z1 bar Z2. And what is this? This is the dot product of X1, Y1, X2, Y2. Manu, shall I erase or students are writing?
Yes, ma'am, you can erase because it will be recorded. They can see later on also.
Okay, okay. So there is a triangular inequality also. That if we have two complex numbers, then modulus of Z1 and Z2, this is less than or equal to mod Z1 plus mod Z2. Why do we call this as triangular inequality? Because these three are represented with the triangle that if we have this is Z1, this is Z2, then this is Z1 plus Z2. So that is why it is known as triangular inequality, because these are the lengths of the three sides of the triangle. And we say the length of the diagonal is always less than or equal to sum of the sides of the other, sum of the other two sides, length of the other two sides. Now, as we have that if this is XY and this is argand plane, this is the modulus, this angle is theta, this is X and this is Y. So from here, you can see that X is nothing but R cos theta, Y is nothing but R sin theta. We can write the complex number in the polar form in terms of R and theta. So from here, when you write X plus iota Y, this is nothing but R cos theta plus iota sin theta. Okay, so later on it was mentioned earlier also that cos theta plus iota sin theta, this is nothing but E iota theta. So we can write this as the complex number can be expressed in terms of polar form, which is R is the modulus, where R is under root of X square plus Y square, and theta is nothing but tan inverse Y by X. This theta, this is the argument. This is the argument of the complex number. So therefore, we can write this as R E iota argument of Z. This argument of Z, this function, this is a multivalued function. Multivalued in the sense that if we have theta is equal to pi by 4, this is same as 2 pi plus pi by 4, 4 pi plus pi by 4. So therefore, this argument of Z, this is a multivalued function, but this is not continuous, which is discontinuous. Along negative real axis. Why? It is discontinuous. This is the real negative real axis. So when this theta approaches to this line, then this value is pi. It is approaching, theta is approaching to pi, but when it is approaching from downwards, it is approaching to minus pi. So that is why that we call that this is discontinuous along the negative real axis. Now, since it is discontinuous along negative real axis, so therefore we write that argument function takes the values. This takes the values in the interval minus pi to pi, close interval. And when we say that argument, it lies between minus pi and pi, this is known as the principal value of the argument. Now we have some rules that if we have two complex numbers z1 and z2, then modulus of z1, z2, this is nothing but modulus of z1 into modulus of z2. But what about their argument? Argument of z1 and z2, the product of the two complex number, it is nothing but argument of z1 plus argument of z2. Similarly, we know this property that modulus of z bar, the conjugate, is same as modulus of z. But what about the argument? Argument of z bar, it is nothing but minus of argument of z. I'm giving all these in brief because we are going to make use of these things later on. Now, what about a disk in the complex plane? If Z is any complex plane, then the set of all those numbers, complex numbers, which are equidistant from this point, it is known as the disk. So how do we define this? D is the disk. It is centered at some point Z0 with radius say epsilon. Then this is the set of all those Z complex numbers such that mod of Z minus Z0 is less than epsilon. Means if this is Z0, this is the set of all those complex numbers here, and this is radius. So this is the disk, open disk in fact. And the closed disk, we use the symbol closed disk. Means the boundary is also included. In the open disk, the boundary is not included, but in the closed disk, the boundary is included. So this is closed disk. This is open disk. This is closed disk. Open disk, this is always an open set. And this is closed set. When we talk about the neighborhood of any point, a neighborhood of a point Z0 in C is an open set containing Z0 So open set here means open disk. So basically we say that open epsilon disk around Z0 is the neighborhood of Z0. As I told you, open disk is an open set. So in complex plane, since we have to move from various sides, as theta moves, we also move, the point Z also moves. That is why we have to approach to this point from various sides. So in this case, we cannot take interval because when you talk about the real axis, then when you talk about the neighborhood, so we consider the open interval here. But in this, if this is theta, there is this is a point xy or z. This is a complex number z. So we have to approach to this point because in case of real, we have to approach to this point from these two sides. But here we have various sides. So that is why we take an open disk around this with radius epsilon and center at z. Then it is the neighborhood of z. Now, basic thing which I want to introduce here is the complex number because main focus is on this. It has several applications. So, complex valued function, which was introduced by Cauchy. That if f is a function from set of real numbers to the set of complex numbers such that the image of the real number, it is a complex number. So it is defined as fx is equal to ux plus iota vx, where ux and vx are real valued functions. When we talk about the continuity of this function f, then we say that f is continuous at x naught. Obviously, f is defined in terms of ux and vx. U is known as the real part of f and v is known as the imaginary part of f. So this function f is continuous at x naught if the real valued function ux and vx, they are continuous at the point x naught. If ux and vx are continuous at x naught, so in terms of complex number, if we talk f in terms of a complex variable z, then we say f is continuous at z naught if given any epsilon greater than 0, there exists delta greater than 0 such that fz minus f of z naught, this is less than epsilon whenever mod z minus z naught is less than delta. So what does it mean? It means that whenever we take the limit as z tending to z naught of fz, its limit is coming out to be fz naught. Then we say the function f is continuous at the complex number z naught, at a complex point z naught. Now, if z is any complex number x plus iota y, obviously this can be written in the ordered pair xy. Then we can define this function fz in the form uz plus iota vz. And since z is in terms of xy, so we can write this in the form that f of xy, x comma y, this is same as uxy plus iota vxy. So when we say that f is continuous, if f is continuous at z naught, which is x naught plus iota v naught, what does it mean? It means u and v are continuous at the point x naught, y naught. Now, what about the graphical representation of the complex valued functions? There is a problem in showing the complex valued function in two-dimensional plane, because you can see that if f is mapping from the complex number to the complex number, and we have that this fz is equal to uz plus iota vz, then obviously if we take z to be x plus iota y, then we have that f of x plus iota y, this is same as ux plus iota y plus iota v x plus iota y. So we have four variables. These are x, y, u, v. So we cannot represent this complex function in the Argand plane. So what we do, that we divide these in two parts, that we say that we have domain and range, that if suppose we write fz is equal to w, then this is where we are representing x and y. This is known as z plane, and its image, if f is a function, then its image is going to w plane. So this is u and this is v. This is known as w plane. For example, if I say that fz is equal to e iota theta, this is nothing but this is a circle with center 0 and radius 1. So we are saying that if we have a complex number here xy, or this complex, the z plane, it is mapped to the unit circle here with center 0 and radius 1. So in this way, we represent complex numbers in two different two-dimensional planes. because we have 4 variables here. So this is the graphical representation of complex valued functions. Now next is the main concept, which is the analyticity of the complex valued function. Next, we talk about differentiability and analyticity. So if f is a complex valued function in real variable x, then f dash x naught, the derivative of this function at a real valued function point x naught, it is the differentiability of u and v at the point x naught, where u dash and v dash are the derivatives of u and v respectively. But when we talk about the function f defined from c to c, so if f is defined in terms of complex variable, if z is x plus iota y, and we have that fz is nothing but uz plus iota vz. When we talk about the differentiability at the point z naught is your x naught plus iota, then f dash of z naught, this is nothing but limit delta z tending to 0, f of z naught plus delta z minus f of z naught divided by delta z. Now, where delta z is nothing but delta x plus iota delta y. If you express this, then what you get, that your f of z naught, this is nothing but u of x naught y naught plus iota v times x naught y naught. And what about f of z naught plus delta z? This becomes u of x naught plus delta x, y naught plus delta y plus iota v, x naught plus delta x, y naught plus delta y. When we talk about this, so from here we have that f of z naught plus delta z, you take f dash z naught, which is limit delta z tending to 0. If you substitute the value, let me write it directly. So when we substitute the values, this is u of x naught plus delta x, y naught plus delta y, plus iota times v, x naught plus delta x, y naught plus delta y, minus u x naught y naught plus minus iota v, x naught y naught divided by delta x plus iota delta y. Now, if this delta z tends to 0 along x-axis, when it tends to 0 along x-axis, what happens to delta y? It will be 0 because it is approaching along x-axis. There is no role of y. So delta y is equal to 0. So what we have, if delta z tends to 0 along x-axis, then we have delta y is equal to 0. If delta y is equal to 0, you substitute here. Then this becomes limit delta x tends to 0, because we have delta x plus delta y. This is already 0. So delta z reduces to delta x. So ultimately we have delta x tends to 0. So this is u x naught plus delta x y naught, because delta y is 0, minus u x naught y naught plus iota times v x naught plus delta x y naught minus v x naught y naught divided by delta x divided by delta x. And what is this? Because here y naught is fixed. there is a change in the value of x. So this is nothing but the partial derivative of u with respect to x. And the second one is the partial derivative of v with respect to x. Similarly, when delta z tends to 0, along y-axis. So what happens when we are moving towards 0 along y-axis, delta x is 0, because we are just moving along x-axis. So we have then delta x is equal to 0. Then delta z becomes what? Iota of delta y. So if you again substitute here in this equation, what you have, and this is nothing but your f dash z naught. So we are getting that f dash z naught, it is nothing but limit delta y tends to 0, u of x naught y naught plus delta y minus u x naught y naught plus iota v x naught plus x naught y naught plus delta y minus v x naught y naught divided by iota times delta y. So what is this? This is nothing but the derivative, because now x naught is fixed. It means this is the partial derivative with respect to y. So this is 1 upon iota delta u by delta y. Here iota cancels. So it is delta v by delta y. This can be written as minus delta iota delta u by delta y plus delta v by delta y. If you just compare 1 and 2, because both are f dash z naught, so what happens? If you just compare, you are getting that real with real. So delta u by delta x. Here the real part is this. So delta v by delta y and delta v by delta x, it is equal to minus delta u by delta y. Okay, so these are known as Cauchy-Riemann equations. So what is the conclusion from here? That if f is differentiable at z naught, then Cauchy-Riemann equations are satisfied. But this is only the necessary condition. What about the sufficient condition? That can we say that if the Cauchy-Riemann equations are satisfied, then it is differentiable at z naught? Yes, we can say, but we need an additional condition that the partial derivatives, this delta u by delta x, delta v by delta y, delta v by delta x, delta u by delta y, these are continuous. So this is sufficient if the partial derivatives are continuous at z naught. Okay, so then it becomes if and only if. Cauchy-Riemann equations, as I told you, that they play a very important role when we check the differentiability of a complex valued function. So based on it, we have the concept of analyticity. There are different names for this in different books. It is known as holomorphic function also. Sometimes it is known as a regular function. These are same names. These are synonymous to each other. So we say the function f, it is analytic in a neighborhood of z naught if f is continuously differentiable everywhere in U. So what is the difference here? That here analyticity we cannot consider at a point. For this we need a neighborhood. We always talk about the function is analytic in some neighborhood of z naught. We are not saying that function is analytic at a point. Whereas when we talk about the differentiability in reals, we say that it is differentiable at a point. Okay, this is the main difference here. Now, if a function is analytic throughout the complex plane, then it is known as entire function. Means analytic in C, the entire complex plane. So simple example is that fz is equal to z. This is entire because it satisfies the Cauchy-Riemann equations, or directly also you can prove this function is entire. It is differentiable everywhere. Let me give a quick proof of this that we take by the definition. This is f of z naught plus delta z minus f of z naught divided by delta z. So this is coming out to be, because it is fz is equal to z, so this is delta z minus this divided by delta z. So it is coming out to be 1 every time. So therefore, this z0 is arbitrary point. It is differentiable everywhere. So it is entire function. But when we talk about this fz is equal to the complex conjugate z bar, this function is not differentiable anywhere. Why? Because when we talk about this derivative at an arbitrary point z0, what happens that this is z0 plus delta z minus f of z0 divided by delta z. If we substitute the value, this is z0 bar plus delta z bar minus z0 bar divided by delta z. Delta z tends to 0. So again, this is delta z bar upon delta z. And what is this? This is nothing but delta x plus iota delta y divided by bar divided by delta x plus iota delta y limit delta z tends to 0. So when it approaches to 0 along x-axis, then delta y is equal to 0. Then in this case, we have this is real only. So we have this is equal to 1. But when delta z tends to 0 along along y-axis, then delta x is equal to 0. You are getting this to be minus 1. Because the angle becomes, once it is theta and another it is minus theta. So we are going to get this minus 1. So you can see the left hand limit. I mean, when it approaches to along x-axis, it is 1. When it approaches along y-axis, it is minus 1. So the limits are not same. Therefore, this function is nowhere differentiable. No. In real analysis, when we talk about the functions, we can have functions which are not differentiable at one point. At other points, it is differentiable. For example, if you consider mod x, this is not differentiable at x is equal to 0 or at the origin, right? But otherwise, it is differentiable. But here in complex analysis, we have the function is differentiable only at one point. Other points, it is not differentiable. It is frequently, we have so many examples in complex. One example I want to give, that if we consider fz is equal to mod z square, which is same as x square plus y square. And this, if you compare with uxy plus iota bxy, so here what we have, that it is only real, so it is x square plus y square, and vxy, this is equal to 0. When you find its partial derivative with respect to x, this is 2x, and the partial derivative of v with respect to x is 0, and partial derivative of v with respect to y, it is 2y, and the partial derivative of this is equal to 0. So you can see that the Cauchy-Riemann equations, CR equations, they are satisfied at z is equal to 0. Otherwise, they are not satisfied. It means that this function is differentiable only at the origin. Fz is differentiable only at z is equal to 0. Okay, otherwise it is not differentiable. So this is a frequent scenario in complex which is not available, or which is rarely available in real. Another important aspect of analytic function is the relation with the harmonic functions. We say if there is a function h, this function is harmonic if it satisfies the Laplace equation. What is Laplace equation? That the sum of the partial derivatives, second order partial derivatives with respect to x and y, this is equal to 0. Okay. So now we want to show that the real and imaginary part of an analytic function, they satisfy Laplace equation. For example, let us take f to be u plus iota v. This be analytic in some open neighborhood in say u. Then if u satisfies this, means we want to show that u satisfies the Laplace equation. It should be 0. So this is nothing but the partial derivative of delta u by delta x with respect to x, and this is partial derivative with respect to y. But since it is analytic, so u and v satisfy Cauchy-Riemann equations. So from here we have that this delta u by delta x, this is nothing but delta v by delta x. And delta u by delta y is nothing but minus times delta y. This is minus times delta u by delta x. So this is nothing but delta 2v delta x delta y, and this is minus delta y delta x, and this is equal to 0. So it means this u, this is a harmonic function. Similarly, when you take delta 2v upon delta x2, you are getting, similarly, you can prove that v is also harmonic. So from here we have one thing, that if f is analytic, then u and v both are harmonic, right? But we have another concept that if u is harmonic and we are able to find out a function v which is harmonic, and they are parts of this complex function f, then we call this v as the harmonic conjugate of u. And it is not always possible to find out the harmonic conjugate of a function. Now, for example, that how do we find the harmonic conjugate? That if we have a function uxy, which is given as xy minus x plus y, and of course this is harmonic if you find out delta u by delta x, this is y minus 1, and delta u by delta y, it is x plus 1. When you find out second order derivatives, obviously it's 0, 0, so you are getting delta u upon delta x2 plus delta 2 delta y2, this is equal to 0. So it means u is harmonic. But since it satisfies the Cauchy-Riemann equations, so what we have, that delta v by delta x is equal to minus delta u by delta y, which is equal to minus x minus 1. Similarly, delta v by delta y, it is delta u by delta x, which is equal to y minus 1. It means we can integrate, it is a function of x, this is x. So if we integrate, what we have, that v is equal to integration of minus x minus 1 with respect to x, which is coming out to be minus x squared by 2 minus x plus some function of y, because it is a function of y. If you take some function of y, so it is a constant. But delta v by delta y, we want to make use of this. So delta v by delta y, if you take from here, so these are functions of x 0, so you are getting only phi dash y. But delta v by delta y from here, this is equal to y minus 1. We want to calculate actually this constant in terms of y. So phi y is nothing but its integration with respect to y, which is same as y square by 2 minus y plus some constant c. So from here we are getting phi y is this. So what is the value of v from here? V is going to be minus x square by 2 minus x plus y square by 2 minus y. If we have obtained this v, then what is f? So fz can be written as u plus iota v. Your u is xy minus x plus y, and this is plus iota times minus x square by 2 minus x plus y square by 2 minus y. So here, if you substitute z is equal to x plus iota y, then this function reduces to minus iota z square minus 1 plus iota z plus iota c. This is the function fz. So we have obtained the function f where we this function b, this is the complex harmonic conjugate of u. In this way we can find out. Now we can talk about the polynomials also, that if we have two functions f and z, f and gz, these are analytic functions, then their sum, their difference, their product, their ratio, where gz is of course not equal to 0, they are also analytic. We can talk about their derivatives also. Here we have to apply the product rule. When you differentiate, here you have to apply the quotient rule when you differentiate. Now, if we define a polynomial pz, this is of the form a naught x z raised to the power n plus a1 z raised to the power n minus 1 and so on. So this is always an analytic function because fz is equal to z, we just did, it is analytic. So z, its product, z into z into z, this is z raised to the power n is the product n times of z, this is analytic. So sum is also analytic. So therefore polynomial is always an analytic function, and this is in fact an entire function. It is analytic everywhere because fz is equal to z is entire function. And if you want to find out the derivative of this is nothing but, because we can write this as, this is sigma, इसको उल्टा लिख लेते हैं for convenience. So this is an z raised to the power n, and varies from 0 to capital N. Capital N varies from 0 to n. So when you find out its derivative, this is nothing but n z raised to the power n minus 1. So in this case, n varies from 1 to n. In this way, we can find out the derivative. We can always talk about the rational function Rz, which is the quotient of two polynomials Pz and Qz. Since Pz and this Qz is not equal to 0, so when Pz and Qz being polynomial are entire functions, and then Rz, this is also an entire function at those points where Qz is not equal to 0. If Qz is equal to 0 some points, then obviously we eliminate those points from the complex plane. Now, next thing, if Manu, can I have 5 minutes, because I want to tell you something interesting about this function.
Ma'am, you can take.
Okay, thank you. This is another aspect of the Cauchy-Riemann equations. This is something new which I want to tell you, because I wanted to give actually the background to all the students about the complex numbers, then only I can give this. So see, as I told you that the polynomial rational functions, they share the property that they do not depend on z bar, but only on z. Okay. But when we talk about the Cauchy-Riemann equations, we can also find out that when you differentiate it with respect to z bar, not with z. How? I want to give this very interesting property with the help of an example. If suppose I have fxy is equal to x minus 1 minus iota y divided by x minus 1 whole square plus y square. Now, we want to check whether this is analytic or not. So obviously we want to see whether the Cauchy-Riemann equations are satisfied or not. So here, what is x? X, you know, this is z plus z bar by 2, and y is nothing but z minus z bar by 2 iota. I think students know this. This function f, this is analytic if and only if it is independent of z bar, means it depends on only on z, then it becomes analytic. This is another aspect of looking at Cauchy-Riemann equations. How? So we can write this function fxy in terms of this is z bar minus 1, because you can see this is x minus iota y, which is z bar. So z bar minus 1. And the denominator can easily be calculated. This is z bar minus z bar plus 1. Further, you can write this to be z bar minus 1. And if you take out z common from here, z bar common from first and third, it is z minus 1. And this is z minus 1. So basically, this is z bar minus 1 divided by z bar minus 1, z minus 1. So this cancels. So it is 1 upon z minus 1. And if you talk about, if you write this to be uxy plus iota vxy, then from here, the real part of this function, it is nothing but x minus 1 upon x minus 1 whole square plus y square. And vxy, the imaginary part is minus y upon x minus 1 whole square plus y square. Okay. When you take its partial derivative, I'm writing it directly because of the lack of time, but you can calculate easily. This is x minus 1 whole square plus y square divided by x minus 1 whole square plus y square whole square. And this is equal to delta v by delta y, because this function is independent of z bar. So we can conclude that this is this satisfies Cauchy-Riemann equation. And similarly, delta u by delta y, if we calculate, this is coming out to be minus 2 x minus 1 into y divided by x minus 1 whole square plus y square whole square. And this is equal to minus delta v by delta x. Right? But when we want to, so Cauchy-Riemann equation, and if you calculate delta v by delta y, you will get the same. So Cauchy-Riemann equations are satisfied, CR equations are satisfied. So you can have that, since this, we can conclude from here that this function is independent of z bar, therefore it is analytic and the Cauchy-Riemann equations are satisfied. So it is proved. But when I say that if, can we write Cauchy-Riemann equations in terms of the derivative with respect to z bar, not with respect to z? So what happens? If I differentiate f with respect to z bar, obviously this is derivative of f with respect to x minus iota y, which is same as delta f by delta x plus iota times delta f by delta y. Okay. So let us break real and imaginary part. You know, f is nothing but, your f is nothing but u plus iota v. So then what happens, that delta f by delta z bar, it is nothing but delta u by delta x plus iota times delta v by delta x plus iota. After substituting the Cauchy-Riemann equations, we are writing this. Plus iota times delta u by delta y minus delta y v. I'm substituting directly the Cauchy. So this is nothing but delta u by delta x minus delta v by delta y. Okay. And plus iota times delta v by delta x plus delta u by delta y. So what happens, that from here we conclude that the partial derivative of z bar, this is equal to 0. Because you can see that these are equal, these are equal. So therefore, that the partial derivative of this with respect to z bar is equal to 0. That is why we say that f is independent of z bar, then f is analytic and satisfies CR equations. So this I wanted to tell, that whenever you have a function which is independent of z bar, directly you can say that Cauchy-Riemann equations will be satisfied and the function is analytic. I hope, Manu, I can finish, or if you want, I can.
Yes, ma'am, because I think the another speaker must have joined.
Acha, then I can stop. Okay, thank you
Okay,
so
ma'am.
much for patient hearing.
Thank you very much, ma'am.
I hope I have explained all the basics. So in the next session tomorrow, I will take some advanced level of this complex analysis.
Okay, ma'am. Thank you very much, ma'am. It is always a pleasure to have you with us, ma'am. The way you have explained the history of complex analysis starting from the 12th century and taking it towards this 21st century was really informative. I hope that the participants were able to learn the basic notations, basic concepts of complex analysis, then analytic functions and Cauchy-Riemann equations. Thank you again very much, ma'am.
Let me stop sharing this.
Yes, ma'am. So I request Coffee to please take some screenshots. Okay, thank you very much, ma'am.
Okay, I leave.
Okay, ma'am. Pooja ma'am, you can start the session. Dr. Pooja and Dr. Meenu ma'am, you can start the session.
Okay, hello. Hello.
Yes, ma'am, you are audible.
Okay. Good afternoon, everyone. Good afternoon, Mittal sir. Hello.
Namaskar.
Namaskar, sir. I am Dr. Pooja Gupta, working as an assistant professor in Department of Mathematics, JC Bose University of Science and Technology, YMCA, Faridabad. It's my pleasure to introduce a great mathematician and a very good teacher, Professor R.C. Mittal, sir. Professor R.C. Mittal, sir, is working as a professor in the Department of Mathematics, JIIT, Noida. Formerly, he was head of the Department of IIT Roorkee. He has obtained his master degree in mathematics from IIT Delhi and also received his PhD degree from there in mathematics in 1979. He has contributed more than 150 research papers in various national and international journals of repute and conferences. Professor Mittal has more than 37 years of experience in teaching to undergraduate and postgraduate students of computer science and mathematics. He has organized many workshops in IIT Roorkee. He has served as an organizing vice chairman, foreign student advisor, co-coordinator of ISC, head of Department of Mathematics, IIT Roorkee. He has also worked as an assistant warden, and chief warden in the hostels of IIT Roorkee. He has been awarded many fellowships like Merit Scholarship and National Science Scholarship of NCR. He supervised 120 master students and guided 20 research students. Currently, he is actively involved in guiding MCA students in their software projects. He has visited many foreign countries like Iraq, USA, Singapore, UAE, Ethiopia, and Dubai. His research interest includes numerical analysis, differential equations, and partial differential equations. Thank you, sir. Now, without wasting much more time, I would request Professor Mittal sir kindly proceed for the lectures. Thank you, sir.
Thank you, Dr. Pooja, for nice introduction. Uh, Dear students and colleagues, at the outset, I am very thankful to organizer Dr. Manu Rohela for giving me this opportunity to give you talks on Taylor series, Lorentz series, and singularity. I will also take tomorrow conformal mapping. Uh, I am very happy to say that this is my second uh, talk in your uh, university. I earlier in the month of April or May gave the talk on C++, and I must say that for this I will appreciate very much the authorities of the your college, Viveka JC Bose College of Engineering and Science, for giving this kind of facilities for the students. I appreciate this kind of organization of talks for the student, for the benefit of the students. I hope the organizers also having some feedback from the students and doing the needful for the sake of the students. Now I come to my talk, so let me share the screen first. So I share the screen. Uh, I don't know, like to site for it. Yeah. Okay. Can you see my PPT, please?
Yes, sir. Yes, sir. It is visible.
So in this talk or lecture, I will cover a Taylor series, proof of Taylor's theorem, examples, a Lorentz series, their examples, and singular points. Now, before I go to Taylor series, I must tell you that Dr. Anuradha Gupta, she was taking about what you call analyticity of the complex function. Uh, uh, Friends, dear students, the last part which she did, uh, day by day Z bar. Normally, I say normally people don't teach in the class, and that is a nice thing she did for the sake of the student. Please keep in mind. I must tell you here that Taylor series is very important as far as analysis is concerned. The subject area in which I work in, numerical analysis, uh, it is very much applicable because whenever you want to devise some numerical method, then you have to take the help of the Taylor series so that you can judge how much error you are introducing. This is from my specialization point of view. But on the other hand, I would also say that a Taylor series is something very important in complex analysis from the point of view of analyticity. You are taught that a function is analytic, then it is having its derivative. But one of the property of a complex function is that if one derivative exists, then all the derivative exists. So there is a school of thoughts in Russia and France. They say that analyticity means if function can be expressed in terms of a power series, then uh, the function is analytic. So what I mean to say is there are two ways you can define. The first way is that if my function is having derivative at the point and its neighborhood, then it is analytic. On the other hand, if I say that if a function is having Taylor series at a point, because when you talk about Taylor series, you are already talking about what you call a neighborhood of the point, because Taylor series is valid in the neighborhood. It is valid in some point and nearby it. And that's why uh, uh, Taylor series and analyticity goes hand in hand. If function is analytic, it will always have analytic at a point, then it will have its Taylor series. On the other hand, if at a point, if function is having Taylor series, the function ought to be analytic. So that is about a Taylor series, which is not equivalent in real analysis, but in the complex analysis, if function is analytic, it will have Taylor series, meaning is that all of its derivative will exist. So uh, if I have my statement, as you know, in the real analysis too, that if function fz is analytic inside a circle with center at z equal to a. So I want to say that function is analytic at the point z equal to a. Then the function can be expressed in terms of uh, a series, infinite series, where fz equal to fa plus z minus a upon factorial 1 f prime a plus z minus a whole square upon factorial 2 f double prime a, and so on. This you know from the what you call your real analysis also, and calculus also. In the differential calculus in the first variable, the one variable also you are taught. So it is a infinite series where an is given by nth derivative of f at a divided by factorial n. Please keep in mind this a I am writing here is a complex number. It's not real number. It is any complex number near z, near z. So I have a circle uh, whose center is at a, and whose radius is I will tell you that what is the radius. It could be as large as there is no singularity in the circle. So once it comes to singularity, then the Taylor series will not be valid because analyticity will not be there. And so the circle radius will be, the radius of convergence of the series will be up to the singularity in the neighborhood of A. So you have a circle, and now I take a point W within the circle. So when I take W point, then I can write my points as Z minus A upon W minus A, because I have taken a point W in the interior of the thing. So I can write, as you can understand, uh, uh, this Z I can write as A plus Z minus A. So A plus Z minus A is the point. Z minus A is something in the neighborhood of A. And so as long as mod of Z minus A is less than W minus A, then Z minus A upon W minus A will be less than 1. And then you understand I can take Taylor series. Otherwise also, if I go in the sense of 1 upon W minus Z, then 1 upon W minus A minus Z minus A, which is equal to 1 upon W minus Z. And this, as you can understand now, when I take W minus Z, it, this I can write h in the form of I take uh, this z minus a upon w minus z, 1 minus z minus a, w minus a inverse, and this by binomial theorem, or otherwise you can write this in the form of what you call uh, a infinite series. So this is an infinite series. Now, if I multiply both sides by factorial 1 upon 2 pi I, because I understand you are not being taught for complex integration, but I need uh, what you call the, uh, integral, Poisson integral formula for doing this. And when I need this Poisson integral formula, then when I multiplied my everything from uh, this is what you call my fz, or I'm writing my fw. So my fw 1 upon 2 pi I fw. So I multiply both sides by fw. Then both sides, because this is my series. So I'm writing fw here. I'm writing fw here, and this series is there. So by writing fw, then it become fw upon w minus z, it become fw upon w minus a. And then I take integral and divide by 2 pi I. So my this series will become 1 upon 2 pi, a contour integral, which contour is given circle, which is given here, where w is here, this is the circle. So I have uh, 1 upon 2 pi a contour C1, along which the integral is to be obtained, and I have my right side, which is nothing but this series. So this series will become, when I multiplied by fw divided by 2 pi I, then I will have this series. Now, please pardon me, because I understand you are not taught uh, Poisson integral formula, and I can't help it. But anyway, you will, in the next lecture or tomorrow, you will understand that this is what you call a Cauchy integral formula, and this Cauchy integral formula will give you the value of derivative. So this says that this is simple formula says, because w minus z. So this is nothing but the value of f at z. So this Cauchy integral formula says to me that the left side is fz. When I take right side, then fw upon w minus a, meaning is that, so 1 upon 2 pi like this is nothing but fa. Here you have w minus a whole square. So it become factorial 1 upon factorial upon 2 pi I is already there. So what I mean to say is, if I use Cauchy integral formula, then this series is nothing but, uh, please get my point here, that this become infinite series. I'm getting w minus a here. I'm getting w minus a whole square here. I'm getting w minus s and so on, w minus a n plus 1. Now this integral 2 pi I, 1 upon 2 pi I contour integral fw upon w minus a n plus 1 dw. This integral is nothing but factorial n plus 1 upon times f n plus 1 w. So this give you at point A the n plus 1 derivative of fw. So what you have from here is that my fz become fa plus z minus a upon factorial 1 f prime a, because definition of the Cauchy integral formula, this become f prime a, this become f prime n, f prime f n plus f prime n plus 1 a, and 2 pi will cancel out there, and factorial n plus 1 upon factorial n plus 1. So my series will become something like fz equal to fa plus z minus a upon factorial 1 f prime a plus z minus a square upon factorial 2 f double prime a, and so on and so on. That is what the proof of your Taylor series is. Now, if I take A equal to 0, as you understand, the series become a Maclaurin series, and my series become then fz equal to f0 plus z f prime 0 plus z square upon factorial to f double prime 0, and so on, and so on. So this is the proof of using Taylor series or using what you call a simple binomial theorem, a binomial expansion. You can have the proof of what you call your Taylor series. Now, if I take some example, then take my first function as 1 upon z plus 1, and I want to expand it around z equal to 1. Then if I take my function fz equal to 1 upon z plus 1, then fz is this. So value of fz at f1 is half. If I take my function as fz, then my f prime will be minus 1 upon z plus 1 whole square. I put z equal to 1. Then f prime 1 is minus 1 by 4. I take again derivative of this because I know that all the derivative will be existing. So f double prime z is equal to derivative of this, that means 2 upon z plus 1 cube upon f double prime 1. Then I put this become please 8. It is wrong, please. This is wrong, please. This is 8. So this become 8, date 8 into divide into 2, so it become 1 by 4. I'm sorry, please. 2 by 8. So this become 1 by 4, and then minus again I take derivative. So this is factorial 3 upon z plus 1 raised to power 4, and the value of f triple 1 at z equal to 1 is 6y8, which is nothing but 6y16, which is nothing but 3y8. So you have the value of f prime, f double prime, f triple prime, and so on, and you can get the value at z equal to 1 at these points. The moment I get these points, I know my Taylor series, that is fz equal to f1 plus z minus 1 f prime 1 plus z minus 1 whole square upon factorial to f double prime 1 plus so on. And now I put the values of my f at 1, f prime at 1, f double prime at 1, and so on. Then my f1 is half. So I put half here. F prime 1 is minus 1 by 4. So this become minus 1 by 4. Then f triple prime, f double prime is 1 by 4. And f triple prime is 3 by 8. So when I put these values and take necessary things out, my series will be 1 minus z minus 1 upon factorial 2 plus z minus 1 upon factorial. This is half, this is minus half, this is plus half, please. This is plus half, and so on, and so on. So some mistakes, I think. There is some mistake. I understand some mistake is there. So no. So factorial 2, so that become 4. I'm sorry, 4. And factorial 3, so this become, that's perfectly right. So you have this series for fz. Now, if I take second example, my second example h, function h fz equal to z plus 1 upon z minus 3 into z minus 4. Now I want to, as you understand, this function will not be analytic at z equal to 3 and z equal to 4. Please understand, if I want to see what is the radius of convergence of the Taylor series, which I just gave you, this Taylor series, then as you understand, the function is 1 upon z plus 1. And this function is not defined or not analytic at z equal to minus 1. I am expanding from 1. That is, the moment my circle include -1, the function will not be applicable for Taylor series, and hence my radius of convergence will be 1, 2, -1, that is 2. So uh, the circle passing through the uh, singularity, the nearest singularity, will give you the radius of convergence. Now, if I take second example, as I said to you, this is not uh, defined, or it's not analytic at z equal to 3 and z equal to 4. And my point under consideration is z equal to 2, where it is analytic. Then the nearest singularity from 2 is 3. So my radius of convergence cannot exceed 1, because uh, z equal to 2 and z equal to 3 uh, and z equal to 4. So my non-analytic points are z equal to 3, or my singular points are z equal to 3 and z equal to 4. And the point under consideration is what you call uh, z equal to 2, about which I want to expand. And hence, my radius of convergence of the Taylor series, which I am obtaining, will not exceed 1, because my nearest singularity is near z equal to 2, which is 1. So if I want to expand as we do in the calculus, I put z minus 2 equal to t. The moment I say z minus 2 equal to t, then z becomes t plus 2. Z becomes t plus 2. And then my fz becomes t plus 3 upon t minus 1 into t minus 2. Now I can take my partial fractions, and by taking partial fraction, this function can be written as 8 upon t minus 1 plus b minus b upon t minus 2, and I get a equal to -4, b, this you can easily find, and b equal to 5. And so my function become ft equal to 5 upon t minus 2 minus 4 upon t minus 1. And the moment I get my ft value, then as we did for the previous case, I can do the same way, or I can write the series in the form of -5/2, 1 minus t/2 inverse. So I apply my binomial mm, expansion, and both the series can be expanded. At the moment I expand both the series, the second series become 4 1 plus t plus t. This is a simple, all of you know, series. So my 4 1 plus t square plus t cube, and my first term become -5/2 1 plus t/2 plus t square by 4 plus t cube by the expansion of binomial expansion of this. And ultimately, I combine the two, and I will get my ft equal to 3/2 plus 11/4 z minus 2 plus 27/8 z minus 2 square, z minus 2 whole square plus 15/9 upon 16 z minus 2 whole cube, and so on. So this is about what you call my second example. My third example is I take rather 1 upon z minus 3 into z minus 1, and I want to expand about z equal to 4. Now again, because the function is well defined at z equal to 4, it is analytic at z equal to 4, and I can take my series about Taylor series about z equal to 4. However, as you can see, my nearest singularity from the point z equal to 4 is, because 4 and distance between 3 and 4 is 1, distance between 1 and 4 is 3. So nearest singularity is 3, and hence my radius of convergence will be 1. I hope you understood my point. So my radius of convergence will be 1, and so my region of convergence will be mod of z minus 1 equal to 1, a circle of radius 1 and center at 4. Now, as we do in the calculus, I put z minus 4 equal to 2, then z become t plus 4. And the moment z become t plus 4, by ft becomes 1 upon t plus 3 into t plus 1. Again, I can take my partial fractions. So when I take my partial fraction, my ft becomes minus half t plus 3 plus half t plus 1. And then you do the needful that I take 3 out. So this becomes minus 6 1 plus t by 3. And this is already 1 plus t form. And then the binomial expansion can be done and series can be obtained. So that's the way the series can be obtained. The only fact you should understand is that if my series is if my function fz is having is analytic at z equal to z naught, then it can always be expanded by a Taylor series in the neighborhood of z equal to z naught. The one of the beauty with the complex analysis is that if a function is analytic, then all of its derivatives are existing at that point. Then question arises, what is the radius of convergence or how long it will be converging? Then it will converge up to the nearest singularity. If that exceed, then you cannot have convergence and Taylor series will not be valid. Now, take the case when fz is not analytic at some point within the domain, and I'm given this domain D in which I want to what you call expand my series. Then in such cases, uh, so my z naught is a point inside the domain D at which my function is uh, not analytic. Then I will take a neighborhood of z naught and I will try to find its expansion. So what I'm saying is that now rather than having a circle, uh, you will be having annulus region where z naught is a point at which it is not analytic. I say z naught is the point at which function fz is not analytic. Then I will take one annulus region having between a circle which is of radius small r and of radius uh, another circle of radius capital R. Then this series can be written because if I take z naught in this region, then it is analytic uh, within this circle, and my expansion will be of the form there will be two power. One will be positive n power, other will be negative n power. So you will be having my fz equal to a and z minus z raised to power n plus n equal to 1 to infinity bn upon z minus z raised to power n. So this is a negative power, and it will be valid for annulus region where z naught is inside the domain of a circle of small radius r, bigger radius small r, and lesser angle of radius r. So you have this kind of situation. You have z naught and you have a smaller circle of radius r, and you have bigger circle of capital R. Now my point is somewhere here, my z naught at which inside the circle is center of the circle, and C is any point of z. Then I can find this integral, Cauchy integral, and I can divide it into two parts, and according to which I will be having a coefficient from the same way as I did Taylor series, I will be getting coefficient in terms of an, which will be having a positive uh, uh, power, and coefficient will be given by this. On the other hand, if I take another part, then it will be having bn, and it will be having negative power, and things will be given by this power. So you have your an and bn given by Cauchy integral formula very easily. So every function at which it is not analytic, you can always have Lorentz series, and it will be having its own application which will come when I discuss singularity of a function. So I take some example. My first example is, so I take my first example as 1 upon fz equal to 1 upon z square minus 3z plus 2. And I am given 4 domain. One domain is mod z equal to less than 1. So this is a circle center at 0 uh, and of radius 1. Then I have another circle domain which is annulus region having radius 1 and 2, center at 0. Then I have a third region, which is a region which is having outside exterior of a circle of radius 2, center at 0. And fourth is center at 1 between 0 and 1. So these are the 4 domain D, and I want to have my what do you call series. Now, when mod z equal to 1, my function is 1 upon z square minus 3z plus 2. And I know, as you understand, this is nothing but z minus 2 into z minus 1. Are you getting my point or not? So this can be written as 1 upon z minus 2 into z minus 1. So I can write this way. And then my series, my function is nothing but 1 upon z minus 2 minus 1 upon z minus 1. And if mod z is less than 1, I can always have my series here. So then mod z by 2 is less than also 1, because mod z is 1, I divide by 2 will be also be less than 1. And I can write my series as fz 1 upon minus 2, 1 minus z by 2 plus 1 upon 1 minus z. And since I can take the binomial expansion of these two functions easily, so because the condition of expansion is defined, so I can write my function in the binomial expansion form, and ultimately the series can be obtained by taking binomial expansion. On the other hand, if I take 1 is less than domain B, where my Z is centered at 0, and my annulus region is of the circles, concentric circle of radius 1 and 2. Then if I see here that 1 by Z is less than 1, very obviously, because 1 is less than mod Z. So 1 upon mod Z will be less than 1, and mod Z upon 2 will be also less than 1. And as we have seen, I can write my series in the form, because I have to see that where is the less than 1. So I write my fz as 1 upon z minus 2 minus 1 upon z minus 1. And when I write this way, I take minus 2 out, so that I can write 1 minus z by 2 form, and 1 minus z by 2 form means my mod of z by 2 is less than 1. So that is, I can take always my binomial expansion of this 1 upon 1 minus z by 2. On the other hand, if I take second term, then I am having 1 by mod z is less than 1. So I have to write in that form. To write in that form, I have to again write this as 1 by z, because I have to write 1 by z. So I take z outside. And so I write this form. Now I can take my Taylor expansion, or what you call your binomial expansion. So I can write the series in this form. Friends, you understand that this is a some kind of Taylor series because there is no negative term. However, when I take annulus region, then I get this term where I will be getting 1 upon z power. And hence, my series will be something like this, which is, you understand, minus half minus z by 2 raised to power minus 1 and 1 minus z raised to power minus 1. And then if I take my expansion, then my expansion will be for 1 minus z by 2 expansion will be 1 plus z by 2 plus z square by 4 plus so on. This is just binomial expansion, you know. And then, or you can say some kind of geometric series. And then this is also, uh, 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 this, I don't know why, this is 1 upon z, please. This is 1 upon z. I'm sorry. I'm sorry. So you have 1 plus half z square by 4, and this is 1 by z, 1 minus. So the 1 minus 1 by z raised to power minus half. So you will be having this series, and ultimately you have your h and you have your b's, and this is the series like. But here you are having the what you call negative power. So this is precisely Laurent series, while this is a Taylor series. Now, if I take uh, my domain as mod z by 2, mod z is greater than 2, that is a circle which is outside the circle of radius 2 center at 0. So I have a domain, my domain is outside the circle of radius 2. And that means my z by 2 is greater than 1, or my 2 by z is less than 1. And so 1 by z will also be less than 1 or less than half. So 2 by z is less than 1, 1 by z is less than 1. I have to use these two criteria so that I can, what do you call, write by series. Now my 2 by z is less than 1, so I have to break the first term in the form of 2 by z and my second term in the form of 1 by z. That is the funda, because I have to take my series which is valid. So when I take first term, I have to write this as z minus 1 minus z by 2, because my function is 1 upon z minus 2, and I take z out, so this becomes 1 minus 2z, and I take z out, so this becomes 1 minus 1 by z. So when I do so, my function is like this. Now, uh, uh, so my function is like, my function is like this. And so what you have is 1 by z into 1 minus 2 by z raised to power minus 1, and minus 1 by z, 1 minus 1 by z raised to power minus 1. Both can be expanded now by binomial expansion. So when I take binomial expansion, condition is already satisfied, and I can write in this form. Now this is truly only Laurent series. There is no positive part. So you have z minus 2 plus 3 z minus 3 plus 7 z minus 4, and so on and so on. And this is expanded at about z equal to 0. Now, one point you should understand, because I am saying this point because you will be taught, but since it has come to here, here the coefficient of 1 by z, that is the z minus 1, is 0. That is, if I take this function fz, then its residue at z equal to 0 will be 0 because the coefficient of 1 by z is 0. So what I mean to say is, when you want to find residue and you take your Laurent expansion, the coefficient of 1 by z will give you the residue. The residue part will be taught to you uh, next time. But anyway, you should have idea from the Laurent series that the coefficient of 1 by z will give you the, the value of residue. Then I come to the annulus region, which is a second kind of annulus region, where by uh, annulus region is by circle is having center at 1. So by I have two circle, one is a point 1 only, and other is a circle of radius less than 1. And then my z minus 2, I have to write in the form of z minus 1. So this is 1 upon z minus 1 minus 1. And this is minus 1 upon z minus 1, which is already there. Now, because the conditions are satisfied, z mod z minus 1 is less than 1. So both series can be, I take negative out, so I can write this as 1 upon minus 1 upon 1 minus z minus 1, and this can be written as 1 upon z minus 1. And hence, I can write in the binomial expansion form, and my series will be of the form minus 1 plus z minus 1 plus z1, because this is the series which I am getting, and my first term will be minus 1, my second term will be plus 1 upon z minus 1, and you will see that they will be cancelling out, and you will be having this kind. So I will not have any part of z minus 1. So it is having finite Taylor series part. It is having a Taylor series part, which is having infinite series. So you have, there is no negative terms at all, no negative terms at all. So this is what your, what do you call, Laurent series of annulus region, which is not valid for 0 and less than 1. So you have this. Now, let me take second example where my fz is e raised to power z upon z minus 1 whole square, and I want to expand around z equal to 1. When I want to expand around z equal to 1, then I have to write in the z minus 1 form. So e raised to power z has to be written in the form of z minus 1. So I write e raised to power z as e into e raised to power z minus 1, because I want to expand around z equal to 1. So my fz becomes now e raised to power e raised to power z minus 1 upon z minus 1 square. Friends, I know that I can expand my e raised to power z1 z minus 1, because it is always analytic function. Is a what do you call? So I can expand it by its Taylor series or expansion of exponential. So my exponential series for e raised to power z minus 1 will be 1 plus z minus 1 plus z minus 1 square upon factorial 2 plus z minus 1 raised to power cube upon factorial 3 plus, and so on. And ultimately, when I multiply by 1 upon z minus 1, which is negative power, I get my Laurent series, which will be something like this. So you have now a Laurent series of e raised to power z upon z minus 1 square about z equal to 1. Let me take another example where my fz is 7z minus 2 upon z cube minus z square minus 2z in the region. This is circle center at -1 and annulus region, where my smaller circle is of radius 1 and larger circle of radius 3. And this is the domain of a circle of radius 3, it's outside. So you have two regions. If I take the first region, then the trick is same. You have to get partial fraction, and from the partial fraction, use binomial expression, and you will get the what you call your Laurent expansion. So you have fz equal to 7z minus 2 upon z cube minus z square minus 2z. And then I can write this as in the form of 7z minus 2 upon z into z plus 1 into z minus 2. Now I have to write this as in the form of a upon 1 by z plus b upon z plus 1 plus c upon z minus 2. And you use your simple knowledge, you will be getting this as 1 by z minus 3 by z plus 1 plus 2 upon z minus 2. So the function fz is written in the partial fraction form. Once I get my partial fraction form, I will look at my domain. My domain is annulus domain, so I am knowing that my region, my expansion will be Laurent series, and I'm expanding around z plus 1. So my denominators have to be written in terms of z plus 1. My function has to be written in terms of z plus 1. So when I write z as in the form of z plus 1, I have z plus 1 minus 1. So this is my first component or first partial fraction. My second is already in z plus 1 form, so I don't have to do anything. And my third is 2 upon z plus 1 minus 3, because I have z minus 2, so this form. And friends, now you see that I ought to have my expansion in such a way that z plus 1 is less than 3. It means z plus 1 by 3 will be less than 1. I hope you understand me. So when I take that form, so my z plus 1, my first region is this. So z plus 1 by 3. So I have to use this property, and 1 upon z plus 1 is already less than 1. So when I write that way, my function will be z plus 1 divided by 1 minus 1 upon z plus 1. So you have this minus 3 upon z plus 1 minus 2. You have 3 into 1 minus z plus 1 by 3. And now you can expand by what you call your binomial expansion. You have your this series, which is what you call uh, a series which can be expanded by binomial expansion. Then I get 1 plus 1 upon z plus 1 plus 1 upon z plus 1 square. The second term will not be changing. My third term will be the series of this, which is 1 plus z plus 1 by what do you call 3 plus z plus 1 by 3 whole square, and so on. So you have your what you call your Laurent series expansion by using binomial expansion. Now, friends, if my domain is what do you call this is first domain, my second domain, is uh, my second domain is z plus 1 is greater than mod z plus 1 is greater than 3, or 3 upon z plus 1 is less than 1. So now if 3 upon z plus 1 is less than 1, so obviously 1 upon z plus 1 will be less than 1 by 3 or less than 1. So I use this property, and ultimately I have to write in the form of 1 upon z plus 1 form. When I write 1 upon 1 plus z1 form, this z plus 1 will not be changing. However, this term is also to be written in terms of 3 upon z plus 1 form. So ultimately, my series become, my terms can be adjusted to write in the required form, so that my Lorentz series in the given domain can be obtained. So when I do so, then 1 upon z plus 1 minus 1 upon z plus 1 raised to power minus 1. So I can take its binomial expansion and I will get this series. This is my second term. And if I take my last term, then 2 upon z plus 1. And then I take my binomial expansion from here, my series will be something like 3 upon z plus 1 raised to power n, where n is going from 0 to infinity here also, and is going 0 to infinity here also. And you can notice, since my domain is exterior domain, my series is what do you call your purely Lorentz series or negative terms. So what is the idea which you get? You are given annulus region. In the annulus region, if something is within the domain, you will have a Taylor series as well as a Lorentz series, or you will be having a two part, one principal part and there is negative part. So that way you will get your what you call Lorentz series. Now let's we come to the last part of today's lecture, singular points, singularities of a function. Now, before I go to what you call how to define the number of singular points, you will be taught that uh, point z equal to z naught is called zero of a function if f z naught is equal to 0. So z equal to 0, z naught is known as a zero of a function if f z naught equal to 0. Then on the other hand, z equal to z naught is called a singular point if the function fz is not defined at z equal to z0, or we call it a pole. I'm deliberately saying a pole because ultimately when you are given Cauchy integral formula, then you will be coming to the pole and singularities. So what I mean to say is there are singular point, some of uh, the singular point are the point at which the function is not defined, or so to say function is going towards the infinity. So if my function fz is of the form uh, uh, pz upon qz, then the function zeros will be given by the zeros of pz, zeros of pz. The similar points of fz will be given by qz because these are the precisely point at which my function f may not be defined. So what is the condition? A point z equal to z dot will be a singular point if qz dot equal to 0, but pz dot should not be 0. If pz dot is 0, then we have to discuss whether it is a singular point or not, or what kind of singular point it is. So pz dot not equal to 0, I'm knowing that it is a singular point. So for the sake of example, if I take fz equal to z plus 1 into z minus 2 upon z minus 3 into z plus 2, then this function is having a simple 0, minus 1, z equal to 2. So z equal to minus 1 and z equal to 2 are by zeros. On the other hand, if I take the zeros of the qz, then I know that z minus 2 is not a 0 of z plus 1 and z minus 2. So z minus 2 and z equal to 3, these are the two singular points of the given function. Now, if is a singular point, then then if function z equal to z naught is a what you call singular point, however, fz is analytic at each point in the neighborhood of z dot, that Z naught an uh, is called an isolated singularity of fz. Otherwise, it is called non-isolated singularity. Please understand what I'm saying. If z equal to z naught is a singular point, however, fz is not defined at z equal to z naught, but defined at each point in the neighborhood of z naught. Then Z naught is called what you call an isolated singularity. Otherwise, it is called non-isolated singularity. Isolated means there is only a single point which is creating problem. Otherwise, in the neighborhood, everywhere it is good. So function f, consider the function fz equal to z square plus 5 upon z into z minus 3 plus z square plus 1. Now, if I see this function, then I know that the point of singularity could be, I say point of singularity could be at z equal to 0, z equal to 3, and z equal to plus minus 1. And I know that at none of these points, the function is 0, the z square plus 5 is not 0. And hence, these are the singular points of the given function. Now, if I take z equal to 0, then if I leave z equal to 0, I do not consider it, then function is analytic in the neighborhood of z, a small neighborhood of z. It is will be analytic. Similarly, at z equal to 3. Similarly, at z equal to plus I and z equal to minus I. And hence, these are 4 isolated singularity of the given function fz. So I have to look at only in the neighborhood, a small neighborhood of the points at which it is not analytic. Now, if I take second function, then my function is cot pi over z. I know that cot pi over z has what you call number of uh, isolated singularity, because 1 upon 10 pi z will give you cot pi over z, and the zeros of 10 by pi over z are precisely the singular points. And so if I take infinite many points, then 10 pi over z will be 0 at points z equal to 1, z, 10 pi over z will be having, suppose I want to find the singularities between -1 to uh, uh, +1, then if I take z equal to, because it should be what you call 0, 10 pi over z will be 0. That is 10 theta equal to 0. That means theta equal to n pi. So you have z equal to 1 over plus minus 1 over n, and n is going from 1 to infinity. So what you have is that z cannot be 0, please understand. Z cannot be 0. So z is plus minus 1 by n equal to 1, 2, 3, and so on. The z is not 0 because, but it is non, z equal to 0 is also a singularity, but it is non-isolated singularity because it cannot be isolated. However, all positive n will give you plus minus 1 by n uh, uh, points which are isolated singularity. So the function fz will be having infinite many singularities, out of which z equal to 0 is non-isolated singularity, while z equal to plus minus 1 over n is natural number. They are infinite many non-isolated singularity. So that's what the function is having. Now, classification of isolated singularities. What we do is that, suppose I am given a function fz, and I want to find what kind of singularity and what are different kind of singularity it has. Then I expand z equal to, I want to know z naught is a singular point. When z naught is a singular point, the function is not analytic at that point. And function is not analytic, that means I choose a domain in the neighborhood of z minus z naught. So I have 0 exclude z naught. So 0 less than, I take a circle of radius capital R at the center at z naught, and I exclude the point z naught. So I know that it will be having a Lorentz series, and Lorentz series going from n equal to 0 to infinity, and this going from n equal to 1 to infinity. Now, the term is called the analytic part, this term. So this is called analytic part, and the second term is called a principal part. As I said to you there, that there is two parts of the Lorentz series. One is behaving for the Taylor series, which is a nice thing. And so that is called analytic part. That is, function will be analytic, that part. And you will be having negative power, which is called the principal part. So I want to discuss the singularities at z equal to z naught. I have my Lorentz series, which has analytic part, which is the well-behaved part, and I have a negative part, which is called the principal part. Now, there are three cases arises. There are three possibilities. The principal part contains finite number of terms. There is no term in the principal part, or there are infinite number of terms in the principal part. So there are three cases which occurring here. The first case is that the principal part contains finite number of terms. That is, my negative power is up to some capital M. After that, all Bm become 0. All Bn become n greater than m become 0. This is my first case. My second case is that my all Bn are 0. There is only Taylor series part, and there is no negative power, or what we call principal part. And my third is it has infinite number of principal part, infinite number. So all these three will give you different thing. Now let's discuss about a first singularity, that is called a removable singularity. If my at z equal to z naught, there is no principal part. There is no principal part. We can remove this singularity by defining fz at z equal to z naught. And so this is called a removable singularity. That is, if I take z equal to z naught, limit fz exists, if this limit exists, then my function is having a singularity which can be removed. For the sake of this, is a popular example. For the sake of example, if I take z equal to 0, then the function is not defined at z equal to 0. However, if I take limit as z minus z naught, then limit z minus z naught, where z naught is 0, sine z upon z is 1. That is, if I define my function f0 as 1, and otherwise fz equal to sine z by z, my function is well defined. And so my singularity is a removable singularity, or as I said to you, that there should not be any any Lorentz series or negative part in the series. Then my z equal to z naught is called a removable singularity. On the other hand, if I have a finite number of parts in the, what you call your series, principal part in the series, that is, there is a what you call analytic part, and you have uh, the finite part in the series, finite part in the series. Then, then Z minus Z equal to Z naught is a pole of order M, because this will give you, uh, if I simplify it, I will be getting only one term in the denominator, Z minus Z naught raised to power M. So M will indicate the order, and Z equal to Z naught will become a what you call a pole of order M. So what you have is, if I take this function Z minus 2 raised to power 4 upon Z minus 2 raised to power 5 plus 3 upon Z plus 2 raised to power 5, then Z is equal to 2 is a pole of order 5. If I take 4 here, then Z equal to minus 2 will be of order 4, or this is a 5, so this will be of order uh, 5. So just is written 5, it should be 4 here only, nothing else. Then essential singularity. When I talk about essential singularity, meaning is that my uh, principal part will be having what you call infinite many terms. Infinite many terms. So my principal part will be having infinite many series term, or my series except the constant is a purely Laurent series. Purely Laurent series. In that case, it becomes an essential singularity. So you have e raised to power 1 by z equal to 1 plus 1 by z by Taylor series expansion. I have e raised to power 1 by z equal to 1 plus 1 by z and so on. And you can see that it is having infinite many terms, and hence z equal to 0 is an essential singularity of fz. So what we have learned? We have learned that if I want to decide what kind of my singular point z equal to z naught h, I take an annulus region excluding 0 uh, in the neighborhood of z. And what I try to find is that I find its Laurent series. When I try to find its Laurent series, it has two parts. One is analytic, other is principal. The principal part is the contribution from the Laurent series. Otherwise, it would have been a purely Taylor series. That is negative power. Now, if you have uh, only Taylor series part, that is analytic part, then it is removable singularity. If you have finite number of part in the principal or Laurent series part, then it takes a pole. And if you have in the Laurent series part or the principal series part, the infinite many terms, then you have what you call uh, what you call a, an agency singularity. So this much from side. I just take an example. Suppose find the nature of the locations of the uh, points. So z minus z sine z upon z square, z plus 1 into sine 1 upon z minus 2. So if I want to say first z equal to 0, and when I take its series, I get only purely uh, Taylor series part or purely analytic part, and hence it is a removable singularity. Then I take second case, and when I take its what do you call Taylor series expansion about z equal to 2, and I see that when I take is Taylor series, is Laurent series, then I have infinite many terms in the series. So when I see infinite many terms in the series, so z equal to 2 is an essential singularity. If I take 1 upon cos z minus sin z, then uh, cos z minus sin z equal to 0 will give you a kind of pole, and this will be putting tan z equal to 0 So you have t z equal to pi by 4, a single point is a pole. So this is not mm, z equal to pi by uh, z equal to yes, 10 z equal to 1. So z equal to pi by 4 is the series pole. So that's what it is. That's all from my side. Thank you very much. Yeah. So do you have any question? Please don't hesitate. I have time.
Anybody has any query? Okay. Thank you, sir. We are grateful for the time and efforts you took to share your expertise and enlightening us with the knowledge of Taylor and the Lawrence series expansions with singularity. It was a pleasure listening you, sir. Thank you so much, sir, from the bottom of heart. Thank you. Thank you so much, sir.
Thank you very much. Thank you very much. Ma'am, I am leaving now.
Okay, sir. Yes, all the participants, you have to join sharp at 2 p.m. Third lecture will be delivered at 3 p.m. Okay, everyone, can you hear me?
Yes, ma'am.
Okay बेटा, अब आप 3 बजे मिलिएगा for third session के लिए.